So this, though, is in a sense for, and I said along an angled slope, but it's really kind of like straight, any kind of straight motion. Whereas the other thing we'll get to in a little bit is curved motion. I don't know if we're going to make it to that today or tomorrow, but ultimately, I'm pushing something in a straight line. And so that's kind of the big jump here. So let's take a look at the problem at hand. So in this case, I'm dragging this kayak along. So of course I want it to move, right? And kayaks weigh like 40 pounds plus the other junk that might be inside them and so forth. So sometimes I'll carry it on my shoulder. We kayaked Mill Creek this weekend, and you got to climb your ass out of that super steep gorge in there. And the goal is like, can you get out of there without stopping, because it's really steep. But I don't like dragging my kayak too much because it is abrasive, and it's dragging along the ground and ripping stuff off. But if you're on the snow, or like I am here, you're sitting in the grass, it's awful nice not to have to carry it. So you put a tether around your waist and just kind of drag it along and so forth. But of course I am moving, right? Like I'm trying to overcome the inertia of the kayak to get moving. And I actually want to walk. I want to make some progress. And so if you're moving, then you've got velocity, position, and acceleration to consider. And that's kind of the idea here. So notice this force of 44 newtons. That's how hard I'm pulling on the kayak, but of course it's up at an angle, right? So I'm not pulling as efficiently. It's not pulling horizontal. And the other thing, just kind of think about for a second, does it make sense if you pull an object? This kind of something that isn't super obvious, I don't think, but it's like, if I pull on this at 40 newtons and it starts to come toward me, does it make sense I'm not pulling anymore? In other words, I pulled at 40 newtons and now I'm not pulling. If I want to keep pulling it at 40 newtons, I actually kind of have to speed up faster and faster and faster in order to actually keep that same tension on it, because it kind of wants to follow me along, if you will. So that's kind of an odd thing. If I pull at 44 newtons and it doesn't move, then we just kind of reach equilibrium, and I'm going, and it's pulling back and nothing happens, and that's fine. But if it starts moving, that takes that pressure off. Does that make sense? So I got to like move again to keep that pressure on. So pulling with a constant 44 newtons is not kind of as obvious as it sounds in dynamics. So I said, okay, cool. Let's see if we can find the distance that will be traveled and the velocity, find the distance and the velocity after 30 seconds. And this should sort of feel like maybe a physics problem that you would have tackled before. But again, this is a little more interesting than a box sitting on a ramp. This is like time and how long is it going to take me to get out of the canyon and how hard is this going to be to do and all that kind of stuff. So, okay, let's see if we can make a little progress with this, armed with these beautiful equations that we have. So one thing that is always good to do to make sure you don't screw it up, especially given the fact that there's some info down here, like the leash is at 38 degrees, the kayak has a weight, or maybe you should say a mass, given how it's labeled, kilograms. This actually should say mass. You understand that? And then there's friction on the ground because I am having to pull it through the grass. And so I want to make a free body diagram just to make sure I'm not missing anything here. So I've got the force of gravity pulling down on the boat. I've got the normal of the ground pushing back, or the force of the ground. They're both forces. And of course, those would be equal. They would be equal in a sense, because if they're not, then the kayak is going to sink into the ground. I mean, this is like a statics question. If it's just sitting there, I'm standing here on the floor and I'm not going into the ground. I'm putting force on the floor, the force putting force on me. So I'm just standing here. If the floor starts pushing harder on me than I am on it, I'm going to start flying up to the ceiling, or I'll sink through the floor. But this is compromised or complicated by the fact that I am pulling at a 38-degree angle with a force of 44 newtons. Is my diagram complete? The answer is no. What is it missing? Friction. What direction is friction going to go? If I'm pulling it to the right, it's always going to be back pointing to the left. So I'll call that the force of friction. And so now my free body diagram is complete, and I kind of only know one thing. I know 44 newtons. And so, you know, what can I do? Well, I actually know the force of gravity, don't I? Force of gravity is, in this case, it would be in metric. It would be, well, isn't force, as we just reminded ourselves, mass times acceleration? And so since my weight wasn't really a weight, it was a mass, I'm going to have to go in there and put 32 kilograms in for my mass. The acceleration of gravity is 9.81 meters per second squared. So I have kilogram meters per second squared, which is a rather complex unit. And of course, that's exactly what we renamed as newtons. So I'll call that 313.92 newtons. And so I actually do know the force of gravity based on how much what my mass is. Remember, if that had been weight, like normal weight, like 180 pounds, it would just be 180 pounds and I'm done. Because that's actually going to cause us some problems in a few minutes. So actually, no more than that force. Now, does it make sense that the kayak isn't moving in the kind of the Y plane? It's not moving up or down. It's not flying into the sky as I drag it along. Therefore, maybe it makes sense to consider this. Let's do the sum of the forces in the Y direction. But in this case, because we are letting it move, then we're saying that is equal to not zero, but mass times acceleration. And I'm sort of careful to say acceleration in Y when I say that. So that's kind of my basic formula. So then I look at this is why my free body diagram is so important not to leave anything out, because then I look at it and say, okay, well, what's going on? What's going on in that world then? So what do I have? Well, I have the sum of the forces in Y. Well, I have NG, the normal of the ground going up. I've got the force of gravity. Maybe I'll go ahead and write that in. Force of gravity going down, but we already figured out that's 313.92. I've got that. And then I got the 44 going up. But of course, it's not going straight up. So I've got to modify it by the sine of 38 degrees. And so there's the sum of all my forces in Y. Now, in the past, we said equals 0, and we figured stuff out, right? But in this case, I'm saying, well, it's not necessarily equal to 0. It's equal to mass times acceleration in Y. Mass is 32 kilograms. But again, the interesting part, what's the acceleration in Y? Well, you might be tempted to say, isn't that 9.81 meters per second squared? The answer to that would be yes, if it wasn't sitting on the ground. You understand that? In other words, it'd be falling. If this was projectile motion, I'd say, yeah, the acceleration of Y is 9.81. But we're saying it isn't going to move thanks to the ground. It's not going to move in the X and Y plane. And so, yeah, that's actually 0 in this case. Do you agree that that's not obvious? And that's the kind of thing where I could easily think that was 9.81. So you see the difference? No different than last time. It's the sum of the forces. Hey, look at it. We have all these Y forces. Isn't that cool? Except for now we're going to let stuff move. Now, in this case, it actually isn't moving in the Y direction, as I said. And so notice that right-hand side of the equation is 0 because it's not moving in the Y plane. It's just sliding along the grass. Kayak pushes down, dirt pushes up. They found a good balance. It's sort of static in the Y direction. So in a sense, it ends up kind of like it was before. Well, this only has one unknown. And so you end up with the normal of the ground. Notice it isn't equal to 313.92. Is my first thought, and I kind of said this out loud a while ago, was then the ground is going to push back the same. But notice you're kind of lifting it. In this case, because I'm pulling at an angle, I'm actually helping. I'm defeating some of that 313 newtons of gravity. 44, if you will, of it is being defeated. Well, 44 times the sine of 38. So when you solve that equation, you get 286.8. Again, normal in G and N for newtons, kind of annoying. Again, this is just a habit I get into because your page ends up getting really messy after a while. Like that question was never asked. It wasn't asked what that force was, but I'm thinking maybe I'll need it later on. Again, one of the best things that you can do is just start figuring out everything you can figure out here. I'm not following steps. I'm just figuring stuff out. I'm going to do a sum of the forces in X and a sum of the forces in Y. I don't need a sum of the forces in Z because I'm not considering this moving any other directions than X and Y. So I'm really just figuring out stuff I can figure out. And I don't know if I'm going to need this stuff later. Maybe I will, maybe I won't. So I just kind of put some designation around that says, hey, I figured that out. So just like before, some of the forces in X, well, this is going to move. And so this is going to have an acceleration. Well, acceleration could be 0 if I walked at a constant rate. So keep in mind that not moving is acceleration of 0, but walking in cruise control is also acceleration of 0. So if I said something in there about walking at a constant rate, does it make sense that acceleration of X would also be 0? Okay, well, I look at my free body diagram and I say, what do I have going down in X? Well, I've got two forces in X. I've got that 44, but it'd have to be modified by the cosine of 38 to be entirely horizontal. I got that going right. I got the force of friction going left. And then I've got the mass of the kayak times the acceleration in X. I know the mass is 38 kilograms. I'm not too sure about the acceleration of X, and I'm not too sure about the force of friction. So I'm kind of thinking about those. But if I don't know those, then I don't like this equation because it's got two unknowns in it, right? Algebraically, I'm not very happy with this equation. So, do I know either of those? So this is a blast from the past. But remember that the force of friction was equal to the normal force times mu. Mu was the kinetic or the coefficient of friction. So I actually can figure this out. And it turns out, well, I did need to know that normal of gravity. So again, it's interesting that gravity is not 313.92, it's only 286 because I'm lifting it a little bit. So it's not as frictiony. Does that make sense? If I lift it a little bit, then it's going to slide a little bit. I can't get it to slide right now. If somebody lifts it a little bit, even if you can't lift the whole thing, that's going to take something off. And so I do know that normal 286.8. And I was told the kinetic coefficient of friction was 0.1, 10% basically. And so I actually can calculate the force of friction. So I guess that's 28.67. 28.68. And so there's only one unknown left, acceleration of X. And it actually means that I guess it isn't 0, which is kind of interesting, isn't it? So if I crunch those numbers, I end up with acceleration of X being about 0.187. I'm being a little lazy with units, but I am paying attention to them. All my measurements were in feet, all my times were in seconds. Again, this problem only asked me for the distance it'll travel and the velocity. So acceleration of X, I figured it out, but it's like, do I need it? I don't know. So I'm not, for me, I'm not boxing it, I'm just highlighting it. So basically all that work, there's just a couple calculations I have now that maybe I'll need for something else later. I'm making tools out of the existing tools I have. And this gets back to what I said a second ago when I was pulling that chair. Does it make sense in order to maintain 44 newtons of force, you're actually going to have to not just move, but even speed up moving? That's what this is saying. I got to go faster and faster and faster in order to actually keep 44 newtons of force I'm pulling. It's kind of weird. I don't think that's obvious. I find that a little challenging, I guess. Well, and again, I think this is why physics is sort of painful to people, because it's like, now what do I do? Well, remember, you still have your basic laws of how acceleration, velocity, and position are related to each other. That hasn't gone away. That hasn't changed. Anytime anything's moving, there's three components to it: velocity, acceleration, and position. In the previous section, we said if I know one of those, then I can work my way to others, right? And we just figured out our acceleration in x, and so maybe I can use that. So I'm looking at those two equations thinking, can I use my acceleration I just found in x to get my velocity in x somehow? Can I use the position equation there to figure out where I am? Because that's basically what I know. Notice I didn't know anything before. I didn't know speed, velocity, or acceleration. I knew nothing, but at least now I know my acceleration in x, and so I'm kind of wondering, hey, look, the acceleration is the ingredients in a lot of those formulas, and so maybe I can figure some stuff out. Maybe I can work my way around using those two calculus-based formulas, which is kind of rad. So, yeah, go ahead.
Shouldn't your acceleration next be 0.57?
That's probably just rounding. I haven't pushed any calculator buttons because I figured this stuff out before, so I probably rounded a hair different or something like that. But like, I think for those newtons I wrote down, I carried it out to 2 decimal places instead of one like I wrote down. So I think it's actually my fault that that's happening. So it's just rounding. Good question. So if you want to get this stuff, in my opinion, when it started to make sense to me was only when I realized, when I thought of this stuff as just tools. I've said this before, but I just kind of want to keep highlighting it so you'll maybe get better and better, or maybe agree more and more with this idea. But there's just too many steps. I just feel like I'm never going to be able to do anything with this if I don't learn how to think about this more deeply. So I'm just thinking of tools, and that's kind of what my note sheet is there's all your tools. If you see A, then put it everywhere you see it, and just look at it algebraically, and just figure out everything you can possibly figure out, and then you'll just get the answers that whatever the dumb problem is asking, you'll get those plus maybe a whole bunch of other answers. So of course I'm walking across the ground. There's really nothing happening in the y direction. Does that make sense? Notice it was weird that I needed the normal force to help me with x, but what I'm really doing is just walking down the street, right? This thing dragging behind me, trying to hold me back. And so I'm really traveling in x. And so there is no velocity in y. I'm not flying up in the sky. There's no position in y. I'm staying y is 0. And so everything kind of pertains to x. Does that make sense? So I'm even going to write it this way. I'm going to say, okay, cool. Well, then my velocity in x would be equal to my acceleration in x times my time plus my initial velocity in x. And we just figured out that our acceleration in x was around 0.187. What was our initial velocity in x? Was that given in the problem? What velocity did I start at? I don't think I said it here because I was actually just speaking in common sense. But in a book problem, it would say something like, the person starts from rest or something like that. I didn't write it in there just because it's kind of a duh. I started walking. So that's not obvious in the problem, but I didn't have any speed when I started. And so, okay, cool. I have this velocity of x equation, 0.187 t. So now I have an equation that will tell me the velocity if I know the time, or tell me the time if I know the velocity. Well, notice that was one of the givens. In other words, the time was 30 seconds. I want to know my velocity after 30 seconds, because your velocity is going to be changing all the time. So you can't say what is your velocity because it's not constant. You're going faster and faster and faster. And you knew that as soon as you knew the acceleration was 0. So there's no such thing as what's your velocity in x. It's what's your velocity in x at some certain time. So if I say, okay, cool, well, then find your velocity of x when time is 30 seconds. And again, notice the units for that. Just I won't write them in here, but if you take 0.187 feet per second and you multiply by seconds, doesn't that turn into feet per second? So that's kind of cool. So you get about 5.6. Because that was one of the questions I was being asked, and I'm saying, hey, cool, I finally got someplace I wanted to be. So I know how fast I'm going. So this formula gives me the ability to find that speed at any time I want now. So I moved from a constant acceleration that I knew to velocity. Can I also move there from position? Well, again, I'm interested in, I hope you're comfortable with the fact that I can't just write that position equation. I've got to say in X or in Y or even in Z for that matter. So I have 1/2 times acceleration of X times T plus initial velocity, which is in X times T plus initial position. We said already that acceleration of X is 0.187 feet per second. We already decided the initial velocity in X is nothing. And again, I didn't say this, but the idea is you started walking at some point. What's your initial position? You're not going to name that as a mile marker. It's just kind of like, okay, I started up at the bottom of the hill and I'm going to start walking. So in a sense, based on common sense, your initial position is nothing. And so now I have this position equation. All I have to do is, well, it calls for, I guess, just time. So all I have to know is the time now, and I can convert to velocity and I can convert to position. That's kind of cool. So again, I throw 30 in there for time. I won't talk about units, but you can play around with that. This will end up being just in feet. And you get about 84.2 feet, somewhere in there. So in a sense, that first page was brand new. Force equals mass times acceleration. But the second page is something we've known before. And I definitely think kind of seeing this a second time, even though you would have done problems similar to this in physics, I think recognizing that these equations allow you to move between acceleration, velocity, and position. So as long as you know one, you know all of them. Like, I'm pretty good at this stuff. I can't get this problem right unless I just look at the equations I have to work with and start using them. Do you see, in a sense, that that's what we did? I started with this equation right here, figured some stuff out from the note sheet, figured out a few things there that I knew, and then I jumped to another set of equations I know. Really, in a sense, those were my 4 tools, and I made whatever I needed to make from them. There's no particular order to this. This isn't step 1, step 2. Notice, in a sense, I made it look easy because I just happened to do the sum of the forces in Y first, and I figured something out. Had I started with the sum of the forces in X, I would have indeed had these 2 unknowns, and then I would have thought, uh-oh, I don't really know what to do. I may have taken an incorrect guess at acceleration in X and said I wasn't accelerating or something like that. And then I would have said, okay, well, that equation doesn't do me any good, and I would have had to jump somewhere else. But in a sense, we used those ingredients, those highlighted formulas to figure out everything we wanted to know. So just out of curiosity, does this strike you as like easy or hard, or like, I'm sort of curious just based on, you know, what you learned in physics. It was a year ago, you forgot everything and you know nothing, and therefore it's kind of like you never took it. I mean, what does that feel like to you? I want to actually hear what you say. You find yourself going, okay, I think that's study, I can get that, or that's totally easy and it was a waste of my time. I'm actually curious.
I don't think you do.
What'd you say?
I don't think either of us have taken physics, but still got it. But we took physics in high school.
It makes sense if you find one to do that. So.
What do you think?
I feel like calculus definitely helps. You know, taking the derivative.
Mhm.
You don't even need the equations.
Yeah.
They're just kind of fun.
Yeah, it's kind of neat. Okay, well, let's take this up a notch then. What if we jumped to the second problem I give you, which is that skier problem? In a sense now, this problem, and again, this is the equivalent of some box sliding down a ramp in a physics class, but I'm, fascinated by this kind of stuff. I was talking to you guys about mountain biking and kayaking and skiing, and the fun of a lot of those sports is getting airborne. And this is kind of a classical example of that. I got some examples we'll do later in this class where if you have a hill that looks kind of like this, and somebody's going to put a road into it, they end up coming in and basically chopping down and chopping across and then removing that chunk right there. So you end up with kind of that. And that's what a road looks like when it's side hilling, if you will, or trail or anything else. And so mountain bikers will come in here and like make a little jump right there. And then of course this is called a road gap jump. But again, the key is like, don't land there, because that's flat. If you actually jump far enough that you land back down here on that kind of angled part, then you don't take near as much impact, which we'll study later in this class, not as much of a hit and so forth. So I'm sort of fascinated by this concept of, how time works and speed and how it's all connected. I mean, these are all things that are motion. And of course, this is dynamics because we're riding our bike, we're skiing and so forth. So this problem is similar, except for, as I said here, this 180-pound skier is going to ski down this slope for 30 feet and then fly off and land on the flat ground and fracture his tibia. 8 feet is high enough. You probably would be hating it a little bit from that. So let's see, what do we got here? The slope is 30 feet. That's in the problem. So I can see that over there. Notice the 30 feet is not horizontal. It's actually the angle. And then I have this coefficient of friction. Yeah, that makes sense. Skis on snow, there's going to be some friction. And that's it. Like, that's all we know. You just basically start up there with, as you might have learned in physics, all this potential energy. You're like up there high, and now you're going to turn that into kinetic energy. You're going to start moving, cruising down the hill. And so really there's the problem with this question though, is really if I kind of move from the top to the edge of the jump, like for instance, if I call this location A and this location B, and down there I call that kind of location C. There's really two things that are going on. From A to B, you got friction applied to you, and you've got no acceleration, just like we saw a second ago. There's no acceleration that's trying to get you to kind of, the snow is stopping you, if you will, from falling. Whereas as soon as you go from B to C, now you're actually free falling. And so you can't do this as one problem. You got to do it as two separate problems. So notice in the last problem, it was like my legs, the force of my legs were getting the force that caused the kayak to move, right? But what's causing it this time is gravity. So if I was on a flat ground, you wouldn't be moving. But if you put it up on an angle, then you will be moving. So you have no choice here but to kind of start with just AB, and then so let's figure out what happens when I go from A to B. But rather than go immediately into it, I want you to think about that for a little bit. I mean, can you at least picture that it's like, okay, yeah, I got gravity pulling me down, and some component of that 180 pounds will be directed downhill. And then that's actually going to get me moving. And from your own experience, you probably understand that you're going to go faster and faster and faster. You don't actually just cruise control that. You're going to go faster and faster and faster unless you do something about it. In skiing, you increase the friction by leaning sideways, and you stop that progress. Does it make sense if the hill wasn't steep enough that your 180 pounds might not overcome that friction and you would just sit there? So that's interesting too. We haven't done a lot of this, but to make our life way easier, I'm going to call that direction Y and this direction X. Do you understand that you are free to make your axis whatever you want? Like, X does not have to be horizontal. This is going to make my life easier, but it is possible both ways. Now, first thing I'm going to do is exactly what we did last time, which is make a free body diagram so I can kind of figure out what forces are involved here. And I'm going to turn it now, just because I'm used to looking at it this way. So everything is in kind of X and Y. So that's kind of my X as per usual. And what's wrong with this drawing right here? Gravity's going down. Can we tell what's wrong with that? Nice job. That's right. Because I rotated it. If gravity went straight down, then you would not move because gravity's not pulling you down the hill. No component of it is going downhill, but that's exactly right, Ian. Because it is at a 75-degree angle to the ground, then the force of gravity is actually pulling sideways. Maybe you can see it a little more easily now. Now, in this case, notice your force of gravity is 180 pounds. In our system, you're done. That is your weight. That's your force. Weight is force. Don't have to convert it. But given the picture I do, does it make sense? Some component of that 180 is actually heading downhill, and that's what's going to actually cause you to start moving. Well, if it overcomes that frictional force. So let's see, I've got that. And then I've got friction force trying to stop me from going downhill. What's missing on my free body diagram? The normal of the snow. Again, if you don't have that, then this means you're sinking through the snow. You're sinking through the air, so to speak. So you got normal. And remember what's implied in that is that it is perpendicular. And so now that's complete. Now that's got everything. So there are a bunch of forces. Is it possible that all those forces balance and we just stand there? The answer is absolutely yes. But it's also possible that they don't balance, in which case we start moving. And if we move, then we have mass times acceleration, Newton's formula that kind of tells us what those forces result in. So I'm kind of going down the same road that I went before. So there's only 3 forces this time in this figure. So I don't know which ones to do first. I don't really care. I'm going to do some of the forces in X first. So in the last class, we just assumed it was always 0. In this class, we're just not assuming that. We're saying, well, it could be something. Like a minute ago, though, we saw it was 0. Because the acceleration in Y was 0, we saw it was 0. So we're just not assuming that anymore. Maybe things will move. Okay, let's see. What are my forces in X? I got the force of friction going backwards. So that would be negative. And then the only thing I got going forward is that 180, but of course it needs to be modified. Let's see, I guess that would be by the cosine of 75, wouldn't it? So maybe I'll just draw this in here as a vector, but if I draw this, isn't that the force in X and this is the force in Y? So there's all my forces in X, and I've got a mass, and I've got acceleration of X, which again, kind of like last time, I'm not that sure what to do with. Does anybody know what's wrong with that mass though? This is really weird. It's not that actually, because it's, so at an angle is kind of an issue, but it is literally just mass, in other words, just weight or whatever, but that's not a mass, that's a force. You understand that? So 180 is a force, but it's not a mass. Didn't we say force is mass times acceleration? So 180 is not the mass, it's actually the force. What's acceleration of gravity in this world, which is the standard world, not 9.81, but what? 32.2. So it's 180 pounds and it's 32.2 feet per second. So mass is actually 180 divided by 32.2. Isn't that weird? So it actually is asking for mass, a weightless quantity. It's more like a measure of volume or something like that. So that's weird. Like we thought, oh, this is great. I don't have to convert that 180. I don't have to convert that 180 to from mass to an actual force. But this force equals mass times acceleration equation is kind of rad. Like it's something you really got to pay attention to. It's really kind of weird. So this is correct, and I'm not happy with it because it's got two unknowns. And I don't even know if I need this. I don't even know what I'm doing. I'm just trying to figure out what's going on here. I got a bunch of forces, made a free body diagram. I see everything's kind of moving along. Awesome. Maybe I'm forgetting something. Maybe I made a mistake somewhere. I don't know, but at least I've got something written down. Well, now I'm going to switch to the sum of the forces in Y. And also equal to mass times the acceleration in Y. So looking at my free body diagram, I got the normal of gravity pushing up. I've got the force of gravity 180 pushing down, but it's at an angle, so I'd have to modify that by the sine of 75. That's it. Those are my ups and downs. And then I've got my mass, which has not changed, times my acceleration in Y. Again, two unknowns. So, and I've got two equations and two unknowns, but the unknowns don't even match. Does it make sense? I really have two equations and four unknowns. That's not good. The question is, do I know any of those? What's AY? If it is, that means you're actually accelerating through the snow. That's the tricky part of this. So you're wanting to say it's 32.2, and that's in a sense true, but that would only be if you're free falling. The snow is basically saying, no, you're not going to do that. You're not going to go in the Y direction. You're not moving in the Y direction. So since your motion in Y is actually nothing, then this is 0, not 32.2. Again, do you agree that's not obvious at all? In a minute, when we're down here falling through the air, acceleration of Y will happen, and it'll be 32.2. But up here, the snow is saying, no, you're not going to do that. So since we're not moving in Y, it'd almost be like this is a statics problem. The sum of the forces in X is equal to 0. It's not moving in Y. So tricky. Okay, well, that's actually good news because at least there's only one unknown after all in that second equation, and so I can solve that one. And so in this case, notice the normal of G just matches the skier's kind of weight. So I have to go right over here in case I run out of room. So the normal of G, I already worked this out, ends up being 173.9. So I basically am saying normal of ground. I could have said normal of snow or something like that. So basically the snow is pushing back equal to the skier. So you're staying on the hill. You're just not going into the snow. You're not flying up in the air. So that's cool. But what do I do with my original equation? My first equation, I still, since all the unknowns, there was no match at all. It's not like that helps me with the first equation. Yeah, but back to that force of friction equation. Force of friction equals the normal times mu. Since I know mu is 0.2, and that 173.9 normal force right there actually can figure out the force of friction, which, like the last problem, then this is very similar. I should say it's even identical. It's identical to the last problem. The difference, as I said, is just it's gravity that's causing the motion here because you're on a hill, whereas last time it was, you know, a machine, a person, or something like that. So the force of friction then comes out to be 34.8 approximately. I think I'm going to erase this, but if you think back a minute ago, basically friction is pulling 34.8. Remember, this is kind of weird because that's a capacity. It doesn't mean if you're standing on level ground that you're suddenly going to start flying backwards. It's a capacity. If the gravity did not overcome that, then you wouldn't actually move. Remember, going the other direction we said was 180 pounds, but it was actually times the cosine of 75 degrees. So, what is 180 times the cosine of 75 degrees? 180 cosine 75 is actually 46.6. So do you see how the gravity overcame it, but not by a lot? Isn't that interesting? If that had been less than 34.8, then you would just sit there. That's the idea. So the hill was steep enough and the coefficient of friction was effectively small enough that we actually are going to get moving here. So we are going to move in that direction. Isn't that kind of cool? Kind of interesting. So thanks to that calculation, I'm basically going to get a positive number then. When I add that to 180 times the cosine of 75, notice it's figuring out the difference of those two things. Then I'm actually going to be able to calculate the acceleration of x now. And I'll just leave it in blue. So that means the acceleration of x and works out to be 2.11. So like last time, that acceleration of x is sort of the hallelujah moment here. Like, ah, sweet, I've got something. I have something about my motion now. Before, all I had was like angles and coefficients of friction and so forth. I didn't know anything about motion. Now all of a sudden I just found a door into my motion and I got in there by acceleration, which was rather surprising. And now I'm going to be able to convert to, any other thing I want to do, just like before. So let's see what happens. Just in the interest of maybe time here, then I'll say, okay, cool. Just like last time, I have v of x then is equal to acceleration of x times time plus my initial velocity in x. Since we started from rest again, like last time, that's going to be 0. And now I know acceleration is 2.11. So basically I can say my velocity of x is 2.11 times time. That's kind of a cool equation that will allow me to convert. Now notice what's different. Last time I said, I told you the time was 30 seconds. Notice I didn't tell you that here. I could have told you that. But in this case, it's not a time. Like we didn't know what time it was. How long are you going to ski before you fly off that 30-foot cliff right there? That the equation's not that helpful because I don't know v of x or t. So, but again, I'm just writing down stuff that I know. What else do I know? S of x is equal to 1/2 a of x t squared plus v0 of x t plus s0. And like last time, I know this term is going to go to 0. My initial position is 0 because I'm starting at the top. I'm starting at wherever I was. I'm calling that 0. And since acceleration of x is 2.11, I'm not happy with that equation either because I still don't know time. So does it make sense? I don't know time. So how am I supposed to figure anything out here? Anybody have any brilliant ideas? What do I know, or do I know anything? Remember, these model your velocity and position for any time you want. Like in a sense, these equations don't know there's a hill there. But what do we know about that hill? It's 30 feet long.
Could we take our position formula, set 30 equal to 1/2 2
Exactly.
solve for T, plug that back into.
That's exactly right, which is why I think you have to have these important equations amidst all your chaotic work, why you got to have them kind of highlighted like I did with a highlighter or some kind of a, because it's like, these are my tools. I'm just trying to do algebra now. I'm trying to let my math ability help me figure out what to do next. And that's exactly right. Since I know that this is 30 feet, then I can actually solve for the time, which is of course kind of fun, right? To think that I'm basically just sitting there and I kind of do the, now I turn this direction and it's like I'm literally figuring out, considering I know the coefficient of friction. And again, notice as a side note, we are neglecting wind resistance, which actually means it would take a little longer than this. Of course, there's things you can do to change that, right? I can get all nice and wide and really be like a sail, or I can do the tuck for the GS and try to decrease the wind resistance. But that's annoying. So anyway, I plug that in. Oh, finally I have an equation with only one unknown in it. So I can actually figure out the time. If I do that, I get 11.25 feet per second. I'm sorry, I get, what did I write that down? 5.33 seconds. And then of course I can take that and put it back in there for T, and I can actually know how fast I'm going. And of course, that's tied to the 30 feet, right? This isn't how fast I'm going anytime. It's how fast I'm going at 30 feet. So this is basically what speed you're at the end of the jump. So if I throw that back in there, I get velocity of X being 11.25 feet per second.
Cover. I guess my question is, how would we?
Yeah, that's a great question. Anybody have any thoughts on that? Like, what if you decided that was going to be a big thing? And you can probably appreciate if you're going to go way down the hill, quite a ways down the hill, and you actually were pretty resistant to wind, and a person kind of is with a bunch of ski clothes on, you're like a giant sail. That's going to totally screw up this calculation. Does that make sense?
Would you almost treat it like friction?
Exactly. You'd have to come up with some kind of a friction coefficient for wind. And the interesting thing is, and we'll play with this later in this class, but does it make sense that if you, let's say you just started right here, same things on that hill. So you started in a certain spot and then you let yourself ski for an X number of feet, say it was only like 12 feet or something like that. You could actually calculate maybe how much time it would take to get there and so forth. And you wouldn't get there in that time, right? You'd get there later than that by, and of course it would take some pretty sophisticated tools because the time might be so tiny. That's why, a lot of problems neglect it, because maybe it wouldn't make a difference. But I would say in skiing, if you were going to ski like a mile, just standing there like this, it would make a huge difference. If you're going to be 10 seconds late or 20 seconds late or whatever, thanks to that. But you'd have to do something to capture that. Does that make sense? But yeah, that's exactly right. Yes. So one key point in all of this, though, is, as I said, though, that's not really your constant. That's not your constant velocity. It's more like, maybe I should note, this is like at B, like that's your speed and the time to the location B. And so in a sense, because you started at speed 0, basically you sped up and you went faster and faster and faster until you made it to 11.25 feet per second. And if you stayed on that same slope, you just keep going faster and faster and faster. So notice it's kind of interesting. It took 5 seconds. That's quite a while. 1, 1,000, 2, 1,000. Takes a little bit of time to make it 30 feet, but 30 feet is about the distance across this room. And so that's interesting. I started from 0 and I sped up and got to that speed. And so now the world changes. No longer am I going to have an acceleration of y of 0 because the ground's about to drop away from me. So all of a sudden I am going to be accelerating in y for the first time. And I'm going to lose my velocity change in x. Does that make sense? Whatever velocity, this is what we did the other day with because this is just projectile motion now. We've done this. It doesn't mean it's like, oh, it's easy work. It's a piece of cake. But remember, whatever speed you leave at, that's the speed you're going to stay at in the x direction. But now you have an acceleration of y, which is going to start pulling you down, which is why your arc falls down. If it wasn't for an acceleration in y, you would actually just fly through the air in a straight line and just keep flying in the same direction. You see how the world kind of changes? All of a sudden, we got different considerations now. But what's kind of fun about this is the other day, I think it was a mountain bike problem we did. It was like you pedaled to get that speed, but notice in this case, you didn't pedal. You just started higher and then let yourself go and you rolled up to that location. And so now you have a fixed kind of a launch. You have a launch angle that you left at sort of 75 degrees, and you have a 11.25, I think we said, speed, and you're angled down though. You're not jumping, you're actually angled down. So I want to give you a second to kind of think about that. So let's see, we're going to fly from B to C now. And again, maybe you noticed I'm not even reading what the question asked me to do. I'm just figuring stuff out. I use the exact same process we just used. And even though we just moved to projectile motion, I'm still going to be using the exact same formulas. I still have a velocity, position, and acceleration formulas. It's just that what is zero and what is not zero is going to change. That's the only difference. So now I'm going to fly from B to C. So let's figure out what's going to happen there. So there's my initial velocity. And notice it's not in X or in Y, it's at some weird angle right now. And I can put this angle any place I want, but if that angle on the other side of that was 75, 75 plus 15 would be 90. So I'm going to name that angle instead of the 75-degree angle. And of course, I'm doing that because I'm thinking of this as my velocity initial in X, and I'm thinking of this as my velocity initial in Y. So I'm going to break it into those two component parts because we said those behaved independently of each other. Does it make sense? That's all I have at that point is speed. Well, and then of course I'm 8 feet above the ground here, right? So let's see, what does that leave me? That means my velocity of Y would be 11.25 times the sine of 15 degrees. That's my initial velocity in Y, which works out to be, saving a lot of time by making all these calculations ahead of time. Is 2.91 feet per second. And I probably should throw a negative in there. Like I drew the picture with it down, and so I could rely on the picture and kind of see that it's down, but it probably makes more sense to throw a negative in there because I'm actually going down. And the same thing would happen with X. Interrupt me as always if you have questions. 11.25 times the cosine of 15 would give me the initial velocity in X, which works out to be 10.87. So I've said this before, but do you ever stop and just kind of go, does that make sense? Do those numbers make sense? And my thought is, yeah, Pythagorean theorem, if those two numbers should be smaller than 11.25, because that's the hypotenuse. And then because 15 is such a small angle, velocity of X should be really big. And velocity of Y should be pretty small. So they're both less than 11, but one of them is pretty close to 11. Yeah, this kind of makes all kinds of sense. So the question is, do you feel good about this from here? So I've got so we said once you're flying through the air, these two things kind of behave independently of each other. Although we've treated them as independent from each other the entire time. In our last problems, we only had X's to worry about just because we weren't moving in the Y. But now we are moving in the Y. So we're just going to have to do this kind of twice. So I guess I don't know which one to do first, but I guess I did vertical in blue. So let's do the vertical stuff in blue. So I have my initial speed, but that isn't necessarily going to stay the same. So let's see, what do I have in that world? I've got the velocity equation, velocity equals acceleration times time plus initial velocity, but I'm talking about y here. So this is velocity in y, acceleration of y, initial velocity in y. Do I know any of those?
Skip that equation, just go straight to the distance equation.
Yeah, do we need this? I don't know. I mean, that's kind of my point. It's unless you're really good at this, my thought is just do everything. Am I going to need this? I'm not really sure. So we know our initial velocity in y, negative 2.91. Don't we know our acceleration in y? Because this was feet. Remember, the reason this is not 0 is because you can now fall in y. So gravity is accelerating you downward only. And so I actually have an equation for velocity of y. I can know my velocity anytime I want. So velocity and our time are related to each other. It makes sense. There's not an answer to this question because your velocity is going to be changing all the time. So it kind of depends what time it is. Depends what time it is or where are you. You don't just have an answer to this question. And then I wonder, what about the position? What about the position equation? Again, I start by maybe writing out the whole thing. But realizing that I'm working with y, I have to kind of go back and say, oh, that's acceleration of y, that's initial velocity in y, that's the initial position in y. We already said, we agreed that the acceleration of y was 32.2. We already agreed the initial velocity of y was negative 2.91. Do I know anything else? Yeah, notice when you start talking about position, you have to decide a frame of reference. In other words, we got these equations, and so it's like, what are you going to call 0, 0 on the graph? Like, where are you going to place the axis? Are you going to place it right here, like this? This is x and this is y. In which case, your initial position in y is 0, and they're going to fall from there. Or are you going to say, nah, I think I like it down here better? Nah, you say, I like it over here better. I mean, those are the three logical places you could put it. Do you understand that it's okay to put it any place you want to? Doesn't make any difference. I'm going to pick there for no particular reason. If that's the case, then my initial position is 8. I'm 8 feet above what I'm calling 0. So some of you should say, well, that's a bad place to put it then. Why don't you put it up top where you had it up there at B, in which case the initial position is 0. Yep, that totally makes sense. The only advantage of what I did is notice when it hits the ground, y will be 0. So it's like it's going to kind of come out in the wash either way. So you kind of almost have to have that frame of reference written in. There's not a right answer to this question unless you actually have an XY axis drawn in there. So, okay, that means my initial position is equal to 1/2 of 32.2 is 16.1 t squared minus 2.91 t plus 8. So the cool thing about those two equations is they're totally based on time. But that's also kind of not cool because I don't know what time is. Like if I knew if it's something like you're going to fall through the air for 50 seconds, then I would be able to plug in 50 and know exactly where I was, again, barring wind resistance. But I don't know time. And so, what do I do? What do I do with this? Can I do anything with this? Do I know anything? Do I know anything that allows me to get started here? It's not 2 equations, 2 unknowns. It's 2 equations, 3 unknowns. If you're taking Math 261 especially, which it sounds like some of you are, that concept of anytime I have 3 equations, 3 unknowns, bing, there's 1 answer to it. But I have 2 equations and 3 unknowns. That's not good. I can't solve that. So I don't know what to do. Do I know anything here? Remember, these model your flight through the air. Ding, 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 ding. Time is constantly changing. Velocity is constantly changing. Position is constantly changing. So it models everything. And it actually doesn't stop there. It just keeps going forever.
But you know, S of Y is going to be 0. That's our.
That's exactly right. We are interested in this point in particular. Like that's what this problem all derives around. Is like you're going to land right there. You're not going to just keep on going. So I don't really care about, what time and what velocity and so forth that I am through here, position. I'm particularly concerned about this location. And that is something I know something about. I don't know time there. I don't know speed there, but I do know my Y position is nothing. So I would be stuck with this, except for I can sort of say, now I'm concerned with S of Y being 0, which means, that means I'm going to be able to solve for t. And once I solve for t, then I could work my way back up to the previous equation and know my velocity. So I can know everything. So keep in mind, it made sense that there wasn't an answer from these 2 equations because this modeled your position and speed everywhere on that flight. So now when we go back and say I'm concerned about a particular location or a particular time or a particular speed, then I could actually sort of figure everything out. As soon as I know one of those 3 unknowns, then I can use 2 equations, 2 unknowns and find everything I want to know. But it makes sense that I wouldn't know that before then. Notice that that's kind of an interesting problem to solve because if you stick 0 into that, what is your mathematical thought about what you see written there? When you solve an equation that looks like that, what should be your thought if you're mathematically strong? Yeah. This is a quadratic formula problem. And incidentally, I did screw something up back here. Kind of something subtle that I just was looking over at my notes and realized. What's wrong with my acceleration here? There's a direction. It's not a number. You don't have to change anything. But what direction am I accelerating? I'm being pulled down, not up, because I put a positive number, 32.2. That means I'm going up. I'm not really going up. I'm going down. So that should be a negative 32.2 that I put in there, which means there's a negative here and a negative here. That was a mistake. Do you have the quadratic formula programmed into your calculator? It's a good thing to have because again, we don't care about this stuff. We just want the answer, right? So if I stick that into and I don't care, like use the quadratic formula the slow way. If you do, you end up with 2 answers to this. You get negative 0.8 seconds and you get 0.62 seconds. Why is there 2 answers to that? If you look back up here, why would there be 2 answers to that? That doesn't make any sense. Why would the time be negative? Well, keep in mind, a parabola goes forever, right? I mean, the problem does not know that that's a little chunk of a parabola, but doesn't that parabola just keep going? So if you went back in time, it's kind of like you got shot as a projectile in this direction from the ground. So we're going to ignore the negative time one, but that's why there's 2 answers to this. There would be. There's 2 places where that parabola would hit that axis. So that's just kind of cool to consider. So awesome. I'm interested in this 0.62 seconds. And now I can go back to that V of Y equation and say, cool, what is V of Y at 0.62 seconds? If I plug that in for T, I get, and again, I don't even know if I need this. I just think it's kind of cool that I can figure it out. I get, so I don't know what I get. I don't see that I wrote it down anywhere. So negative 32.2 times 0.62 minus 2.91, got 22.87. Stop and make sense of that. Does that make sense? What makes sense about it, or maybe doesn't? It's very important to notice that's at sea, right? That's your speed. It's not always your speed. It's your speed at sea, beneath the ground. So what makes sense is you were already going negative 2.9 seconds and you got gravity pulling on you. So you're going to be speeding up. So I'm going faster negatively. That's about it. I just expected it to be bigger than negative 2.91. If it had been negative 13, I would have thought, oh yeah, great. If it had been negative 40, oh, yeah, awesome. So are you going to get hurt here? Does 22 feet per second mean something to you? I would say the distance from here to there is about 22 feet. If I went from here to there, 1 second, and then go off. Doesn't sound too good, does it? Remember, this is just in Y though. Don't I also have a speed in X? Like this isn't actually the speed you hit the ground because it's coming in at an angle. This is actually even worse than this. So anyway, that's all what's going on vertically. I wonder what's going on horizontally. So I have all the same things, all the same equations. Velocity equals acceleration times time plus initial velocity. It's just that this is acceleration in X. This is initial velocity in X. What do I know about that equation? Do I know anything about it? I know my initial velocity in X. We figured that out earlier. That was 10.87. What else do I know, if anything? What is it? Now you're thinking back, you're in a different world now. Excellent thought. But it's zero because nothing is getting you going downhill. Back between A and B, you did have an acceleration. But in this case, because you're flying through the air, that's nothing. So basically what this is saying is whatever your velocity in X was initially, it's just going to stay that way. Again, not really because of wind resistance, right? But notice we're only in the air for 0.62 seconds. Does it make sense? It actually makes sense to neglect wind resistance here. 0.5 seconds of whatever that force is isn't going to do much. So it's fair to neglect wind resistance here, I would say. It's just not fair if we fell like parachute style and we were like, jumping off a cliff and we went like for 80 seconds or something like that. Well, now it's not realistic. And so that's kind of cool. So I know my initial velocity in X, my velocity in X is just what it is. Velocity in X is just 10.87 feet per second. It always is. What about my position? Again, notice it's not two different equations. I only have very few tools here. I have really just two tools. And the sum of the forces business. I don't have that many tools. But this is specific to horizontal. So it's S of X, acceleration of X, initial velocity of X, initial position in X. Would you agree from our original graph that our position in X, because of where I put this, my position in X is nothing? Because I started right underneath B, and so I have no initial position in X, which Again, I don't think is obvious. So my initial position in X is nothing. We already said your acceleration of X is nothing. We said your initial velocity in X was 10.87. So armed with all of that, position in X is equal to 10.87 T. Lots of other junk is missing. And so do you agree that we know the time was 0.62 seconds? So I can throw that in there and I can actually know my position in X. So I'll say S of X at 0.62 seconds and I get 6.7 feet for that. So basically I flew through the air. I fell 8 feet, but I flew through the air 6.7 feet. I know how much time it took me to get there. And again, I don't even know what question was being asked here. I just figured out everything. I know time. I know my speed in X. I know my speed in Y. I know where I landed. I know everything. So whatever you want to ask me, I know the answer to it now because I know everything. So what was I asking? Determine the total time, not and distance D for his ride. Notice the distance D is coincidentally, we just figured out that was the 6.7 feet. So that's kind of cool. I knew the time from the AEB, that was 5.33 seconds. And then I add 0.62 to it. So I get, what is that, 5.95? And of course, that should make a little bit of sense. Like, why was the other one so long? Well, it was 30 feet long. So we spent sort of a lot more time going 30 feet than we just spent going, 8 and 7 feet roughly. Six seconds, this will all be over. I was standing on top of the fourth chute once when I was pretty young, like 20, 28 or something like that. And I've always wanted to just jump the fourth chute at the bowl and just tuck it straight down. But if you screw that up, you're just going to get mutilated. And I was thinking exactly, not this, because I didn't understand this that well, but I was just thinking, if I just do it, like whatever happens, it's going to be over in 6 seconds. I'll have done it. Like even if I crash, I'll have done it. I didn't crash. And I haven't done it again.
Yeah.
Frightening.
It's only gonna take 20 seconds. It's the longest 20 seconds.
Just a side note here, but with respect to velocity, does that make sense? That's your velocity vectors. You're going horizontally 10.87 when you land. You're going vertically, we figured out earlier, negative 22.87, which is why I drew it down. Does it make sense that if you did the Pythagorean theorem, moved your 10.8, I'm sorry, your 22 point, this is going to matter later on in this class. I didn't ask anything about this, but these are just things I could have calculated. So if I went back here and said, okay, then that's actually your velocity right there. Your velocity is not 22.87, it's not 10.87. Those are your X and Y components of it. So if I did Pythagorean theorem on those two numbers, actually I do want to do this because it seems cool. And you can appreciate, like, this is a major part of how accidents work. Like if you crash into people and so forth, the speed you were going determines how much injury and stuff there is. So the fact that you can calculate that velocity when you hit is totally going to determine whether you break your legs. Like that'd be you don't care about the time. Who cares? You don't care about where it is. 50 feet away, who cares? What I care about is how fast was I going when I hit, because that's going to determine whether I get mutilated, right? So later on in this class, we're going to talk about how to, move from that to force, how to move from velocity to force and energy, like how, because you've got to basically absorb that with your leg muscles, right? Just like catching something like this. You got to absorb that with your leg muscles. If your legs are strong enough, your joints are strong enough to absorb that speed, then you're going to be okay. The other thing that's interesting is because that's coming in at an angle, the only velocity actually that really matters in that is actually the 22.87, because that's the one that's coming down perpendicular to the ground. So although I figured out my actual speed, because it's coming in at a glancing blow, I'm not going to have to absorb the whole 25. Really, it's just the 22.87. That's what I got to absorb. It's kind of like the equivalent of a free fall and just landing at 22.87, 23 feet per second. So could I do that?
Yeah. That would only account for your initial impact, right? Because then that 10.87 will matter.
That's just going to slide you along. In other words, while you're kind of going crash like this, you're still going to be going that way, and you might tangle up your arms and skis and get hurt as a result of that too. But the did I break my legs is going to be because of the 22, not the 25, because they really do act independent of each other. So that's just kind of cool. So my advice with this stuff is go back over this and really study it, because this is the kinds of questions I'm going to be putting on the test. And you can appreciate that's really cool. You just own that whole situation and look back to what we knew at the start. What do we know about this? We knew how much the dude weighed. We knew some measurements of this scenario, which of course, determine things. And then we knew something about the friction coefficient of ski on snow. And we own that entire problem. We know everything that's happening. We know how long it takes, where it is, speed, everything. This is kind of cool. This is awesome to know.
How would we do total distance though? That's the answer.
Oh, awesome question. Total distance. So I'll volunteer for the 30 feet, and then you guys got to figure this out. Does anything come back from calculus as to arc length? There's a cool formula I'm about to screw up. It's something like this. I'm almost sure it's that integral, something like that. It's like arc length. This is Pythagorean theorem. Because when you're flying through the air, does it make sense? This is a tiny bit of x, and this is a tiny bit of y, and the Pythagorean theorem of that would be that little miniature hypotenuse. Well, see, this is a curved distance. How do you measure curved distances? You don't with a tape measure, but you do with calculus. The only downside is you actually have to have an equation for that, and you can find an equation. The equations we did were based on motion. They're not y equals x equations. They were like y and t equations. But if you took your position equation there, your s of x equation and your s of y equation, your two position equations, and got rid of t, so it was just y's and x's, you would actually have this equation. And then you could take its derivative, square it, add it to 1, and find the integral from, well, I guess that would be x's of 0 to 6.7, right? Isn't that how far we flew in the x direction? And you would actually have that distance, and then you could add it to 30. So you could even know the distance, but it would take some calculus. And again, you'd want to cheat to get this integral, because taking that integral is oftentimes really hard, if not impossible. And I think this, almost every problem you make up like this, if I even have this equation right, which I'm 99% sure I do. You can't really do these too often. And of course, it would be very near. I got to shut up and let you guys go, but does it make sense? It would be, if that's 6.7, then you could do Pythagorean theorem to get that distance right there. And then the curved distance would be just a hair over that. So you could kind of check to see if you got it right. So if you want to, in other words, if you think, I'm going to erase this, but if you think of this as just x equals gobbledygook t squared, not s of x, but just x. And then the other equation, the s of y equation, gobbledygook. Replace this with y, gobbledygook t squared. Does it make sense? You could solve those so that there was no t in them. So you just have an equation with x's and y's. Well, then that'd be the equation of this parabola right here. Then you could do that to it, and you would actually know that distance. Obviously, extra credit if you want to tackle that, because it's kind of a cool problem. Okay, as usual, shut up, Doug.